Question number 5. Consider the differential equation dy by dx equals 1/2 sine pi over 2x times root y plus 7. And let y equals f of x be the particular solution to that differential equation. And it passes through the point f of x, f of 1 equals 2. So at point 1 and 2. So I've kind of highlighted that in green here. And the function f is defined for all real numbers. So part A says a portion of the slope field for the differential equation is given below. Sketch the solution curve through the point 1, 2. So basically to sketch the solution, we just follow the slope lines. We're using the slope lines as direction, and that green point I've given here is a point that we're going to use to kind of draw this. So we're just going to use that slope line. It's going to kind of point up towards these slopes here. It's going to follow this slope line here like this. It's pointing down, 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 maybe down to here. Follow the slope lines. And again, we can see that as we hit one of the lines, we just kind of follow the direction which those lines are headed. Okay, so we're going to have a solution that looks something like this. It's not going to be necessarily exactly like this, but all we're doing is following the slope lines the best we can, and that's what they're looking for. For part B, it says, write an equation for the tangent line, tangent to the solution curve in part A at point 1, 2. And use that equation to approximate f of point 8. So basically what we're doing is we're going to come up with the equation of this tangent line. So I'm going to draw this tangent line in a different color. So the tangent line is going to cut through this kind of like that. And we're at x equals 1, and we're going to approximate the coordinate at x equals 0.8. So we're going to be approximating it on the red line, but we're approximating a blue coordinate with that red line. So we're going to use linear approximation, which means we need to come up with the linear, that tangent line equation. We're going to use a point slope form of this equation. So to use a point slope form, we need slope and an x and y coordinate. Well, we've been given the x and y coordinate. That x and y coordinate was at 1 and 2. We just need to figure out the slope. So to figure out the slope, I'm going to use that differential equation. I'm just going to plug in 1 and 2 into that differential equation. So it's going to be, the slope is going to be equal to 1/2 sine of pi over 2 times 1, and then 2 plus 7. So y is equal to 2. And when I plug that all in, I'm going to end up with a slope of 3 over 2. So that looks about right. If I take a look at visually, it looks about right. That's my slope of that red line. And so the equation of that line, the linear approximation line, is going to be y equals the slope of 3 over 2. And I have my coordinate at 1, x is 1, and y is 2. Okay, so I'm just going to even color code this part here, and that is my slope. So I've come up with my linear approximation line, and then I'm going to use that line to approximate f of x, or f of 0.8. So f of 0.8 is approximately equal to the y value on that line when x is 0.8. So when I plug that in, I'm going to end up with 0.8 minus 1 plus 2. Working that all out, I'm going to end up with 1.7. Okay, so y is equal to 1.7, and that looks about right when I take a look at my graph. Somewhere around there, it's going to be 1.7. And it looks like it's a pretty good approximation considering the slope. That slope, probably that tangent line, follows that blue curve fairly closely when we are close to the point x equals 1.